Here we have a ball inside of a rotating tube that has no friction and spins with a constant omega, and the ball rolls down the tube and then exits the end. Let's start with our free body diagram, where if this is rotating down with an omega, call that theta, and here's our mg. Here we have a p. And we'll assume that it's up, that the ball rolls out slowly and it supports it. And without friction, that's really the two forces that we're looking at. Let's break the mg up into components. That's theta, that's theta. This is mg cos of theta and mg sine of theta. This is the r hat direction, and in the direction of omega, we'll call that the theta hat direction. So if we take a look at this in the r hat direction, we have mg sine theta is equal to m r double dot minus r omega squared. The m's drop out, and if I reverse the order here, we have r double dot minus r omega squared is equal to g sine theta where here we have a second order ordinary differential equation. It's linear and it's non-homogeneous, because that's not equal to 0. So our technique is that we have actually two parts to the solution. So the solution, our general, will be a homogeneous part plus some particular part. And the reason for the homogeneous part is you could think of this as being equal to g sine theta plus 0. So part of this function can generate the old 0 that we've seen before, and then part of this function also has to generate this new part as well. So that's our model. So let's look for the particular part first, and the particular solution needs to generate this function. So we're going to assume that it looks something like that. So for our particular, we'll assume that it's some a cosine of omega t plus b sine of omega t. And r dot then would be negative a omega sine of omega t plus b omega cosine of omega t. And r double dot will be negative a omega squared cosine of omega t minus b omega squared sine of omega t. Now to check this solution, we're going to take that and we'll plug this into here, that into there, and see what it takes for our function to generate this particular part. So doing that, we get negative a omega squared cos of omega t minus b omega squared sine of omega t minus omega squared times a cos of omega t minus omega squared b sine of omega t equals g sine of theta. And keep in mind that since it rotates with constant speed, that theta is equal to omega t. That's a constant. So these are all thetas in here as well. Now looking at this cosine term and this cosine term combine to give us a negative 2a omega squared cosine theta. And then these two combine to be minus 2b omega squared sine of theta is equal to g sine of theta. Now, from here we can see that a has to be 0. There is no cosine term over here. And for this to be a valid solution, minus 2b omega squared has to equal g. Therefore, b will be negative g over 2 omega squared. In which case, that is a valid solution for our particular. So our particular, we find, is negative g on 2 omega squared sine of omega t. Let's take a look at the homogeneous part. For the homogeneous portion of this, we need this function to be equal to 0. And we looked at this already. We know that Cosh and Sinh, the hyperbolic trig functions, will satisfy this homogeneous equation. So let's use those. So we have then that our homogeneous equals c sinh omega t plus d cosh omega t. So with that, we now know both parts of our general solution for this event. So let's assemble those. So our general will be c sinh of omega t plus d cosh of omega t minus g over 2 omega squared sine of omega t. We can take the derivative of this to get the velocity, and we'll get c omega cosh omega t, where the derivative of sinh is just cosh, and we'll get d omega sinh omega t minus g on 2 omega squared omega cosine of omega t, in which case one of these omegas will cancel. And then r double dot be c omega squared sinh omega t plus d omega squared cosh omega t plus g on 2, when we bring out the other omega, sine of omega t. Now we can look at our boundary conditions to find these constants. And we know that if we look up here, at t equal to 0, the ball was at the center and it wasn't moving, and it slowly will start to roll out as this bar rotates down. So our boundary conditions then are that at t equal to 0, theta was 0, r was 0, and r dot, which is v, is 0 as well. So up here we have this is 0, sinh of 0 is 0, cosh of 0 is 1, sine of 0 is 0. So everything drops out, and we find that d is equal to 0, which then tells us that we don't need these terms here. If we plug in our second boundary condition, this is 0, cosh of 0 is 1, sinh of 0, that's gone, cosine of 0 is also 1. So from there, we find that c omega minus g on 2 omega is equal to 0. So c is equal to g on 2 omega squared, where now it's positive. So that will give us our final solution, that r is equal to g on 2 omega squared, if we factor that out, times sinh of theta minus sine of theta. Taking this one step further, we can find that the velocity now as g on 2 omega squared. Sinh will be cosh of theta, and it'll kick out an omega, minus omega cosine of theta. And we can bring this omega out in front, in which case it will cancel with that. And that's the velocity as a function of theta, which is one of the things we were asked to find. Find the speed. That's an interesting word, isn't it? Speed. Speed is not the velocity. It's the raw speed of this as it exits the pipe. Well, think about that. As it exits the pipe here, we're going to have a speed of VR, but we'll also have a speed of v theta. And we need to put both of those together, and that will be the actual speed at 90 degrees. R dot at pi on 2 will be g on 2 omega cosh of pi on 2 minus cosine of pi on 2. Cosine of pi on 2 is 0. Cosh of pi on 2 is 2.509. So at 90 degrees, r dot at 90 will be 2.5 g on 2 omega, whatever those values happen to be, and that's VR. And v theta will be r omega. So the speed will be the square root of these squared, 2.5 g on 2 omega plus r squared omega squared. Next, we're asked to take a look at the normal force. And the normal force we assumed was acting upward, and that is as the ball rolls out slowly, we're supporting it on the way down. So notice that that's in the negative theta hat direction. So let's see if we can figure out what this normal force would be. Let's take a look at the sum of the forces in the theta direction. Now this is the positive theta direction here. We have mg cos of omega t minus p is equal to m to r dot theta dot plus r theta double dot. And since this is rotating with constant speed, alpha is 0, we end up with solving this for p, that p will be mg cos of theta minus 2m omega r dot. And we've solved this for r dot already as well, so we'll bring that over. And we'll get p is equal to mg cos of theta minus 2m omega g on 2 omega cosh theta minus cosine of theta. And let's see, some of this cleans up a little bit. Omegas go. Interesting, we have an mg and an mg. This minus we can bring inside, as that'll be negative, and this becomes a positive. So you have an mg cos theta plus an mg cos theta, so p will be 2 mg cos of theta minus mg cosh of theta. We can check this just to see if it makes sense. At theta equal to 0, we get that 2mg minus mg is equal to mg. And that makes sense. The ball's sitting inside the tube with an mg down and a p acting up just to support it. And for p at pi on 2, 90 degrees, cosine goes to 0, cosh goes to 2.509, and there's our solution for that. Also note that it's negative, which tells us that the p-value has turned around, and when we're at the bottom here, it's actually pushing on it. It's opposite of the direction that we had guessed before. So at some point it goes from supporting it to pushing on it and accelerating it. There's a turning point in here, which would be interesting to try to find. Where is p equal to 0? And that would be our turning point where it goes from acting up to acting down and pushing on it. Right, so here we have a negative p, then we're going to have a positive p. If we look at our function, we basically need these to equal each other. So 2mg cos of theta needs to equal mg cosh of theta. The mg's go, and that becomes our question. Now this in itself is also interesting. So let's plot this. So we're looking at when 2 cosine of theta is equal to cosh of theta. So cosh of 0 is 1. And we know that it goes like this. And the cosine function would normally look like this, except it has an amplitude of 2. Which will have them crossing someplace, and right there, at that theta x, let's call it, that's when they'll be equal to each other. So this is a complex equation. We can't really just take the arc of both sides. So we could do this by trial and error. Just take a guess for theta and keep guessing and going back and forth. Or we could use a series to estimate it. And I'd like to look at this series method for solving this, just out of interest. So if you look in the back of your text, you'll find that the cosh of x is 1 plus x squared on 2 factorial plus x to the 4th on 4 factorial dot 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 dot. And cosine x is 1 minus x squared on 2 factorial plus x to the 4th on 4 factorial dot 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 dot. And just to get an estimate here, we can get rid of the 4th order ones, and we'll just use these. And that ought to get us at least 2 significant figures out of this. So cosine needs to be multiplied by 2. So we'll have 2 times 1 minus x squared on 2 equals 1 plus x squared on 2, which will give us 2 minus x squared is equal to 1 plus x squared on 2. We can multiply through by 2 again, and we'll get 4 minus 2x squared equals 2 plus x squared. Bringing this over, we'll get 2. Bringing that over to here, we'll get 3x squared. So x is the square root of 2/3. And if we plug that into cosine, we find that the cosine of the square root of 2/3 is about 47 degrees. So it turns out right around 47 degrees, about halfway down the sweep, the P force will flip over. So here's 90 where it exits. And fairly close to where we're showing it, right here, P would go to 0 as it switches from supporting the mass to pushing on it further down as it accelerates it down through here. Now we could also ask the question, as this is rotating and the ball comes out, if the tube were exceptionally long, is it possible that the ball might stop and return again on the upswing? And to answer this question, really we'd like to know, can r dot go to 0 again once it leaves? Does it ever stop? And to understand that, we need to look at this function here. And again, I'd like to plot it. So the Cosh function starts at 1 and goes to infinity. Cosine normally looks like that. So at 0, we get 1 minus 1, which is 0. It's at rest. But anytime after that, they never meet again. So never stops. We could also look at the motion here. We plot this at sinh of 0 is 0. And that goes to infinity. And sine of 0 is 0. Because it's negative, it's going to go like this. And if we add these two together, we'll get a curve that looks something like this. And ultimately, it converges in such a way that the sinh of theta dominates. That would be called our steady state solution, where t is going towards infinity over a long time. And then down here we have a dynamic or transient response, which is only important in the first cycle or so, and then it diminishes very quickly. Thanks for watching.